All right. So what are we going to do this semester? We're going to talk about functions, and we're going to talk about functions a lot. So it would be a good idea, I think, to start the semester off by reviewing what functions are. So that is what we're going to do. And this first section on function review, I probably won't finish it today. And that's okay, because we'll pick it up on Wednesday, because it's important that we get the review of functions down so that we can move on to the remaining 5 chapters. So in chapter 1, we're going to review what functions are, and then we're going to talk about specific types of functions. And those specific types of functions are linear functions. So if you were to graph it on a coordinate plane, which we'll review here in a minute, you would see that that function forms a straight line. And then we'll move on to other types of functions. And we'll talk about quadratic, and we'll talk about exponential and logarithmic. And then we'll talk about higher degree, polynomial, and then rational functions. So we'll continue our discussion of functions throughout the semester, but we're going to review them this morning and then probably Wednesday morning also. So chapter 1, there we go. On functions, graphs, models, and linear functions, we're first going to review what functions are, and we're going to talk about models. And why do we care to model the world? Well, because that's what human beings do. That's what we do. We ask questions and we want answers. So one of the ways we get answers is by modeling the world that we see. And when we model the world that we see, then we can use those models to make predictions. For example, yesterday, they said there was like a 70% chance of precipitation. That comes from a model. So they've modeled the weather, and any particular day that had the same conditions that yesterday had, 70% of the time, we got precipitation. So that's how they figure out that percentage is from a model. Well, mini models. They have lots of weather models that they use. So do they want to model so they can make predictions? Of course. Okay, then we're going to graph them. We're going to actually look at a graph briefly today also. Then we'll look specifically at linear functions, and we'll look at the equations of those linear functions. So we can take an equation to describe what that linear function is. And we're actually going to look at one of those today also. So skip ahead. Preview of upcoming attractions, if you will. All right, so in section 1.1, we're going to first look at the ways you can define a function. You can define a function using a table of values, you can graph it, or you can use an equation. And just because you have a table of values, or just because you have a graph of values, or just because you have an equation, doesn't necessarily mean it's a function. So we need to define what a function is, and then we can use that definition and look at a table, look at an equation, look at a graph, and determine if that what we see, that table, that graph, or that equation, is actually a function. And we'll talk about domains and ranges. That if we have a function has a set of inputs, things that you can put into the function, and then the function does something. And then it sticks stuff out. Well, those have names. The inputs are the domain and the outputs are the range. We'll talk about that a little bit more in a little bit. We'll create a scatter plot using temperature data. Why not? It's kind of apropos to use temperature data right now. And then we'll look at function notation. And in mathematics, mathematicians come up with certain notation that as soon as you see that notation, you know exactly what it's referring to. And function notation is one of those things. If I see that F in that parenthesis and that X, I know for sure that the person who wrote it is talking about a function. And then we'll look at a real world example. And that is typically what we do in this course. What differentiates this course from algebra is how we apply it. We apply the things that we learn in this course way more to real life than they do in algebra. In college algebra. College algebra is somewhat more theoretical because we're expecting those students to move on in STEM. We're expecting them to take trig and expecting those students to take calculus. So because of that expectation, we do a little more theoretical stuff. But this course is very practical. Okay, let the slide catch up. So there are several techniques to show how Fahrenheit degree measurements are related to Celsius degree measurements. In the United States, we use Fahrenheit. And I'm not sure that there are a whole lot of other countries that use Fahrenheit. I think we're kind of exclusive in that realm. Most everyone else uses Celsius. Now, one of the ways we can compare Fahrenheit measurements to Celsius measurements is looking at a table that compares the temperatures. So, one of the things they did when they set up the Celsius scale of temperature measurements is they designated 0 degrees Celsius to be the temperature at when, I can spit it out, when water freezes. And water freezes at 32 degrees Fahrenheit. So why did we get ice on the roads last night? Not necessarily because the air temperature was below 32, but because the ground temperature was below 32. So as soon as that water hit the ground, it froze. So 32 degrees Fahrenheit is the temperature at where water freezes. That corresponds to 0 degrees centigrade. Water boils at 100 degrees centigrade, or in Fahrenheit, that's 212. So there you can see those two relationships on this table. And then we've got some other measurements in degrees Celsius and their corresponding degrees in Fahrenheit. Minus 20 degrees Celsius is minus 4 Fahrenheit, etc. So this table describes the relationship between these 7 degrees in Celsius and Fahrenheit. So it is specific to these 7 measurements. And there are 7, right? 1, 2, 3, 4, 5, 6, 7. All right, so let's move on. Oh, and this is called data. Okay, let's talk briefly about what real numbers are. So real numbers are this broad category of numbers that include all the rational and irrational numbers. So later in this semester, when we talk about quadratics, if they're not real numbers, then they're imaginary numbers. So in that chapter, we'll talk about this thing called imaginary numbers. I just love how mathematicians came up with this stuff. But anyway, real numbers encompass pretty much all the numbers that we deal with. And a rational number is a number that you can write as a fraction, and an irrational number is a number you can't write as a fraction. So if we look at a number line, every single solitary point on this number line is a real number. And every real number I can plot on a number line. So a number line that encompasses all the numbers with 0 in the middle, going to the right and going to the left indefinitely, all those points on that number line can be identified as a real number. Conversely, if it's a real number, you can plot it on this number line. So that's what real numbers are. Real numbers are the numbers that we deal with mostly in the real world. Okay? So there's this guy named Rene Descartes. He was a French philosopher and mathematician. And he is the philosopher that coined the phrase, I think, therefore I am. That is Rene Descartes. And the prevailing myth about the rectangular coordinate system is that Descartes thought of it when he was sick in bed as a child, and he was watching a fly cross the ceiling. And it occurred to him, looking at the ceiling in his room, which is a plane, and a plane, you could pick up a piece of paper right now. That piece of paper is a plane. So it's 2 dimensions. And he thought to himself, I could describe the position of the fly on the ceiling as it moves from the corner of the room. So he could give it coordinates and specify its position based on a corner. And that's how he came up with the coordinate system, supposedly. They used to call this the Cartesian coordinate system, named after Rene Descartes. So what he says is, we can take the number line and add a second number line to it that's perpendicular to this one. And then they're going to have 4 corners, which represent the corner of the room. So let's do that. So I'm going to create my vertical axis, and we rotated it, and we're going to say that this horizontal axis, we're going to call that X. That's a very typical variable to use for the values on the horizontal axis. And then the vertical axis, we're going to call that Y. That's very typical to call the values on the vertical axis Y. There's nothing sacred about that. It's just typical. And the numbers to the left of 0 on the number line are negative. We know that for sure. And the numbers to the right of 0 on the number line are positive. We know that for sure. But the numbers above the x-axis on the y-axis, we're going to call those positive. It kind of makes sense that going up should be positive and going down is going to be negative. So from there, we have the rectangular coordinate system, and we can plot any point on a plane using coordinates x and y. For example, I could plot the point 2, 3. So 2, 3 would be 2 in the x direction, 3 in the y direction. I could put a point on this coordinate system and call that 2, 3. So when we're talking about functions, as you saw in the earlier table, we were talking about comparing the relationship between 2 things that can vary. Temperature in Celsius can vary. Temperature in Fahrenheit can vary. But we showed a relationship between those 2 variables. So we created this pair of numbers. So for example, 0 compares to 32. 0 degrees Celsius is 32 degrees Fahrenheit. So we've created this pair of numbers that shows the relationship between degrees Celsius and degrees Fahrenheit. So we've created a set of ordered pairs, a relationship between these 2 things that can vary. So just some information about the coordinate system. FYI, we divide the coordinate system into quadrants. We start, the first quadrant is where both x and y are positive. So everything in this first coordinate, both the value of the first number in your ordered pair and the value of the second number is positive. And then we go counterclockwise around. I don't know who decided that. Somebody decided that beyond me. So I can actually plot then, based on this, I can take all those points that we had in the table that showed the relationship between the degrees Celsius and the degrees in Fahrenheit. I can create an ordered pair and I can plot this on that coordinate system, and I can get a picture of what it looks like. And a picture is worth 1,000 words. Okay, so each point in the rectangular coordinate system corresponds to an ordered pair of real numbers, x and y. The first number in each pair is called the x-coordinate, and it denotes the distance and direction from the origin along the x-axis. And the second number in this ordered pair is called the y coordinate, and it denotes the vertical distance and direction from the origin and the y on the y-axis. Now, we didn't use X and Y when we were talking about degrees centigrade and degrees Fahrenheit. We use C and F, and that's okay. That's okay. This is in general, this is what we use. Typically, the horizontal axis we call X and the vertical axis we call Y. That's not sacred. It's just a convention that we typically use. The first number in that ordered pair represents where you go in the horizontal direction, and the second number represents where you go in the vertical direction. And when we pair these numbers to show their relationship, we pair these numbers inside parentheses separated by a comma. That's the way we do it. So when you see two numbers in mathematics inside parentheses separated by a comma, typically we're talking about an ordered pair. You do need to know the context of what you're talking about, but that's typically what we're denoting. That's an ordered pair. That's showing the relationship between two numbers in mathematics. All right. So that's what we did. So we have our table of values. Negative 20 degrees Celsius represents or is related to negative 4 degrees Fahrenheit. So we created an ordered pair that describes the relationship between the degrees Celsius and the degrees Fahrenheit. So the ordered pair is minus 20 minus 4. We put those two numbers inside parentheses separated by a comma. And you'll notice that we put something outside this list of ordered pairs. We've got these things we call braces. And braces simply tell you that this is a set. That's all it tells you. So this relationship, let me get that out of the way. This relationship that's represented in this table between degrees Celsius and degrees Fahrenheit, we can create a set of ordered pairs that relates those two values. So negative 20, negative 4, negative 30, 14, negative 5, 23, etc. And that is a set of numbers. It's a set of 7 numbers showing the relationship between Celsius and Fahrenheit. So you can graph this. If it's an ordered pair, the first number represents the direction and magnitude you go on the horizontal axis. And our horizontal axis is degrees Celsius. And why they decided to make horizontal C, I don't know. They just did. In this particular example, the horizontal axis is degrees Celsius, and then we get the degrees Fahrenheit from the degrees Celsius. So the vertical axis is degrees F. Okay, so that first ordered pair is negative 20, negative 4. So we're going to go negative 20 in the horizontal direction. So we're going to go over to negative 20, over to the left from the vertical line to negative 20, and then we're going to go down 4 units. So we're going to go negative 20 units to the left and 4 units down. And we're going to plot that point. And then we have negative 10, 14. So we're going to go negative 14. So we're going to go to the left 14, and then we're going, negative 10, sorry. We're going to go 10 to the left, and then 14 is positive, so we're going to go up. And that's the second point here. At this point, and this point, and then we have what? Negative, I can't see it because I don't have my glasses on. Negative 5, 23. So we're going to go 5 to the left and 23 up. And then 0, 32, we're going to stay on the vertical axis, and we're going to go up to 32. 25, 77, we're going to go to the right 25 and up 77. 50, 122, we're going to go 50 to the right and up 122. And then 100, 212, we're going to go 100 to the right and up to 212. And we get this graphical representation of this table. So we have a table, and from that table, we created a set of pairs of numbers, a set of ordered pairs. And then from that set of ordered pairs, we graphed it on the coordinate plane. And we get a pictorial representation of this relationship between degrees Celsius and degrees Fahrenheit. And boy, howdy, is this important. Holy cow, is this important. that we can show the relationship between two variables, both in a table or in a table by a set of ordered pairs, and then graphically. Holy cow. I always feel like, I say sometimes to students, I say in class, I wish y'all should go, oh, how important is this? This is like critically important. And I just recorded me saying that. But this is the essence of functions, that we can take the relationship between two numbers and demonstrate that relationship by a set of ordered pairs and by a graph. So this is the graph, and it looks like a line to me. Doesn't it look linear to you? Looks pretty much like a straight line, by the way it is. Okay, so this graph defines a function. Okay, well, what makes it a function? With a set of Celsius temperatures, which we call inputs, which we also call the domain. So the domain of a function is its set of inputs. So in this case, it would be the degrees Celsius, and a set of corresponding Fahrenheit outputs. So we input the degrees Celsius and we output the degrees Fahrenheit. So for minus 20 degrees Celsius, we get minus 4 degrees Fahrenheit. The outputs are called the range of your function. So the input, what you input, which was degrees Celsius, is the domain. What we get from the output, what outputs is a degrees Fahrenheit from degrees Celsius, and that's the range of the function. A function will give the Fahrenheit temperature measurement F that corresponds to any Celsius temperature measurement C. And we can define that using this equation. So this equation shows the relationship between degrees in Celsius and degrees in Fahrenheit. So if I know the degree in Celsius, I can plug that in for the variable in this equation, and I can output the degrees in Fahrenheit. So I can input degrees Celsius and output that temperature in Fahrenheit. So we've described this thing called a function. I'll get into more detail why this is defined to be a function in just a second. But we can define this function by just a table of numbers that shows the relationship between the two sets of numbers, one set being in the domain and the other set being the range. So that table of numbers showed us a relationship between the domain and range of this relation. We also graphed it, and we can see the relation between the degrees Celsius and the degrees Fahrenheit by just looking at the graph. But we can also define a function using an equation, which is typically the way we do that. We normally describe a function as an equation. You're in algebra. That's what you're going to do. You're going to use equations to describe things. We're going to use equations to model real-world situations. So that's an equation that relates degrees centigrade, degrees Celsius, with degrees Fahrenheit. And maybe you can see that if C is equal to 0, what happens to that first term in that equation? It goes away. And so the degrees in Fahrenheit would be 32. If C is equal to 0, F is equal to 32. You've shown the relationship using that equation between degrees Celsius and degrees Fahrenheit. Now, in our example, if I were to draw a line, which let's see if I can do this reasonably decently. If I were to draw a line, and let's say I just draw a line that continues on this way, so I put arrows on it. If I draw a line that way, I'm probably implying things about this function that may or may not be true. Why is this a function, though? Let's talk about that first. This is a function because anytime I input a value for C, the domain and input, I output only one thing. So 0 degrees centigrade represents 32 degrees Fahrenheit. It doesn't represent 32 and 40. So 0 degrees Celsius is exactly 32 degrees Fahrenheit and 32 degrees Fahrenheit only. That's the only value you get as an output. So when I input something into a function, I get one and only one output. That's what makes it a function. If you output more than one thing, which certainly could happen in a relation in mathematics, that's not a function. So if I input one thing and I output one thing, it's a function. So if we only consider in our example the degrees Celsius from -20 to 10 to 100, excuse me, then that would be the domain of this function. Now, when I drew my line, I implied something that's not necessarily true. In our particular case, our table started at -20 degrees Celsius and ended at 100. So our domain is the values from -20 to 100. And the way I drew the line is misleading. It doesn't continue to the left and to the right. Now, theoretically, it could. I mean, I could certainly find the Fahrenheit temperature for -30 degrees. I could do that. But in the context of the example we're looking at, the domain of this function starts at -20 and it ends at 100. And the way we represent that is using an inequality. We say that the temperature in Celsius is between -20 and 100 because of the context of the problem that we're defining. We said we started at -20 and we go to 100. And so the range of our function, since -20 corresponds to -4 degrees Fahrenheit, our range starts at -4 and ends at 212 because 100 degrees Celsius is equivalent to 212 degrees Fahrenheit. So our range is from -4 to 212. And you'll notice we used inequalities less than or equal to. So that's because the point -20, -4 is on our graph. So we include that point in our domain and range using inequalities that include equals. Now that was a mouthful, wasn't there? You have two types of inequalities. You have this type, which is less than, and you have this type, which is less than or equal to. And the less than or equal to includes the endpoint. So -20 is included in our domain, which it is. It's part of our table. So here is our formal definition. A function is a rule or correspondence that assigns to each element of one set, called the domain, exactly one element of a second set called the range. So this correspondence between these two values is a one-to-one correspondence. One element in the domain goes to one element in the range. And how can you define a function? You can define it by a table, which we did, just showing the correspondence, the relationship between your two values. We can define it as a set of ordered pairs, which we did. We took that table that showed the relationship between Celsius and Fahrenheit, and we created a set of ordered pairs that matched the input in Celsius to the output in Fahrenheit. We can certainly graph the set of ordered pairs, as typically in math, if we have a set of ordered pairs, that's exactly what we do is we graph them. And then from there, we can create an equation. That's what this course does. Taking a set of data, can I input it into my calculator and get an equation that models my data? Oh, yes, we can. And then a verbal description. What was the verbal description of what we've done so far? It's a function that describes the relationship between the degrees in Celsius and the degrees in Fahrenheit. Okay, so let's take this example a bit further. So suppose a child's normal temperature is 98.6 degrees Fahrenheit, and the only thermometer available, which is in degrees Celsius, indicates that the child's temperature is 37 degrees. Does this reading indicate that the child's temperature is normal? So if I have the input degrees Celsius, can I determine the output degrees Fahrenheit? And the answer is yes, as long as I know the relationship between those two variables. And I do. I know the relationship based on a table of values, a graph, and more importantly, in this example, I have an equation. And the equation shows me the relationship between the input degrees Celsius and the output degrees Fahrenheit. And what's that equation look like? Degrees Fahrenheit is 9/5 the degree in Celsius plus 32. So if I want to know the output, what is the output? F, when the input is 37. How can I determine that? Well, I can determine that by what I call plug and chug. So the input is C, and can I plug that in right there? Can I plug it in? Plug and chug. That's from OSU, by the way. Plug and chug. Can I plug that in and chug through the arithmetic? And the answer is yes. As a matter of fact, you have a $100 calculator. So I'm saying today, right now, at this minute, there is no reason whatsoever you should ever get a problem incorrect as far as the arithmetic goes. You should never make an arithmetic mistake. Never, ever, 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 ever. Because you have a calculator that will do this for you. So you should never make an arithmetic mistake, ever. Now, can you make arithmetic mistakes? Sure, because you can put the information in the calculator incorrect. You can do that, but your calculator will calculate this correctly if you input it correctly. So there's no reason to get this wrong. You don't have to do this by hand. You can let your calculator do it. And I don't have my calculator open, but I'm going to open it real quick. I have an emulator on my computer. Got the emulator open. Got some interesting stuff in it. So let me go back over here and let me share. All right, so here is my calculator. And I'm going to multiply 9/5 times 37, and then I'm going to add 32 to it. So there's a couple ways I could do this. Because of PEMDAS, I can take the 9 and divide that by 5 and then multiply that by 37. So PEMDAS works. It takes divisions and multiplications from left to right. So it will divide the 9 by 5 and then take that result and multiply it by 37 and then add 32. It's 98.6. Who knew? So you could do it that way because the way PEMDAS works. If you're nervous about that, you have parentheses. You could certainly put the 9 divided by 5 inside parentheses. So you make sure that you do that fraction calculation before you multiply by the 37. You're going to get the same answer. And even on your calculator, you have a fraction button. And so first day of class that we're actually lecturing, I'm going to show you where the fraction button is. So remember where your fraction button is. So do you see the alpha key over here on the left? It's just below the blue second. If I click alpha, Then do you see the y equals above the second? So you go below the second and then above the second. It opens the fraction menu. So alpha y equals opens the fraction menu. And we want number one, fraction. Numerator over denominator. And then I can put 9/5 in there. 9 divided by 5. And then I'm going to arrow over to get out of my fraction. Multiply that by 37. And then add 32. Now, you'll notice that it gave me my answer as a fraction. Well, isn't that cool? Well, that's pretty cool. But I don't want a fraction. I want a decimal. So how do I take care of that? You have this wonderful thing over here called the math menu. So if I click on the math button, so math, number one takes a decimal and converts it to a fraction. Number two takes your fraction and converts it to a decimal. So if I go down to 2, hit enter, it's going to take the 493 divided by 5, my answer, and convert it to a decimal. Sweet. So there is no reason to get arithmetic wrong. Your calculator, that's what it does very well. It does lots of stuff really well. I mean, it does arithmetic very well. So again, to get to my fraction button, I go alpha y equals number one, gives me a fraction. I can multiply that by my 37 and add 32, get an output. That's a fraction output. Take that output, go to the math menu, and number two, convert that to a decimal. So in each one of these, I took an input of 37 degrees and multiplied that by the fraction 9/5, and then added 32 to that result. So I took the input 37, did a mathematical calculation on that input, and got an output. And my output is 98.6. So is 37 degrees Celsius a normal body temperature for this child? And the answer is yes, because a 37-degree input in Celsius is a 98.6 degree output in Fahrenheit. So a perfectly normal temperature for this child. Let me stop share. Okay, so this was 98.6, which is normal. Okay, domains and ranges. Just looking at how we defined this particular function, starting at negative 20 degrees Celsius and going to 100 degrees Celsius, our domain are the 7 inputs. Now, technically, if you want to be technical about this, the input can be any number between negative 20 and 100. But our example, our particular example, the domain includes those discrete values, negative 20, negative 10, negative 5. Those are our inputs. Those are our degrees in Celsius. In our outputs, what we output from degrees Celsius is degrees Fahrenheit. And our outputs, our range, are going to be those set of numbers in Fahrenheit, -4, 14, etc. So this function, the way it was defined, there is a finite number of inputs. We have 7 inputs. From those 7 inputs, we get 7 outputs. Finite means I know where that interval begins and I know where it ends. Infinite means I don't. It continues on forever in both directions. Okay, so the inputs defined by the equation that we got that defined this function, f equals 9/5 times c plus 32. We graph that, we can see all the numbers between negative 20 and 100. So you could find the degrees in Fahrenheit for a degree in Celsius of like 10.2. So anything between -20 and 100, using that equation, you could find the degrees in Fahrenheit, which we did. We found the degrees in Fahrenheit for an input of 37, which was not on our original definition of our function. 37 degrees Celsius was not in that table. But we can use the equation to find by those table of values to find the temperature anywhere in between -20 and 32, -20 and 100. So the way we write that is we say the set of numbers, that is the domain, can be represented by the inequality, and that should be a negative. That negative's up here. It's bad page sentence break there, bad paragraph break. -20 to 100, which in interval notation we describe this way. And don't get too tense about interval notation today, but when we use a bracket and we separate two numbers using a parenthesis, that is the same as that interval. That's exactly what it means. That C is somewhere between -20 and 100, including -20 and 100. And so our outputs, our degrees Fahrenheit, were from -4 to 212, which we could write as the interval that F is greater than or equal to -4 and less than or equal to 212. It's between -4 and 212 inclusive. And we could write that as an interval from -4, to 212 with brackets around it. So whenever we see this kind of notation where we have two numbers separated by a comma with brackets around them, it means the same thing as this interval. But functions, and typically, since we're in a functions and modeling class, our functions are defined by equations that are restricted by the context of the problem. For example, it probably doesn't make sense, even though this equation up here that I'm circling around here, that you can't see, this equation right there, I mean, I could find F for C of -1000. I could do that. That doesn't really make sense in the context of the problem, because there is an absolute zero and it's negative. I don't remember what temperature it is in Celsius. I have it written down somewhere. But there is what's called absolute zero, where the motion of the particles, like atoms, stop. And it's not a -1000 degrees C. I don't remember what it is. So maybe it doesn't make sense to figure out what the degrees Fahrenheit is from -2000 degrees Celsius. That doesn't make any sense. So there is context to the problem that restricts your domain. Okay, so what does a function do? I always use my plastics example. So I have a company and I make widgets. And my company first makes the plastic that I use for the mold of my widget. So I get ingredients that come in and I make the plastic. And then I take that plastic and I put it in a machine that molds my widget. And that is what a function does. It takes this input, plastic, and then it does something to it, molds it, does something, and then it outputs a pretty widget at the end. So X, usually we use X to represent the inputs in a function. So the variable X represents an element in the domain of your function. So in the previous example where we used degrees C and degrees F, X could be any temperature in degrees Celsius. Okay, then you take that input X and you put it in the function. In our function, it took our input, multiplied it by 9/5, and then added 32. Your function does something. And if you're in math, it's going to do something mathematically to your input. Maybe it divides it by 2 and adds 5. Or maybe it squares it and adds 3. It does something to your input, and then it outputs a value. And we use a special notation to represent functions in mathematics. We use this notation here. F parenthesis X. Whenever you see that notation, that means the output of a function f when the input is x. So we input some x and we output some f of x. Now, everybody listening, everybody awake? Y and f of x are exactly the same thing, exactly the same thing. So if I have a coordinate plane and I input an x and I output a y, that y is the same thing as f of x. They're exactly the same thing. So we take some input, we do something to it, some mathematical something, and then we output a y or an f of x. And the reason we use the f of x notation is because when you see it, you know 100% sure that this relationship you see, this equation you see, defines a function. There's no doubt about it, no question. You know it's a function. If someone writes it that way, it's a function. What's a function? For one input, I get one output. One input goes into this machine and I output one thing. If the domain of a function is not specified or restricted by the context of the problem, we assume the domain consists of all the real number inputs that result in real number outputs in the range. The range is usually a subset of the real numbers. It doesn't have to be. The range can be the set of all real numbers. But if you don't know the context of the problem, you assume the domain is everything that you can input for X. Are there restrictions on what you can input for X? Sure, we'll talk about that later. But typically, the domain is any value you can plug into that equation and get an output for. Sometimes the domains of functions are limited to values that produce defined values. And this is what I was talking about. You can't take the square root of a negative number. You can't do that in real numbers. So that restricts what you can input into the domain of a function. And we'll talk about those later. We can use a graph of a function to find or verify its domain and range. We can usually see the intervals over which the graph exists and therefore agree on the subset of the real numbers for which the function is defined. And that set is the domain of the function. We can also usually determine the outputs of a graph by looking at it, and that set of real numbers or that subset of real numbers would be the range. So looking at the graph, looking at where your graph goes in the horizontal direction from the smallest value to the largest value would give us the domain, and looking at a graph in the vertical direction where we go from the smallest value to the largest value would give us the range. All right, so here are your definitions. The domain is the set of all first elements of the function or the inputs. So the domain is the value that you input into your function. So let me just draw a picture. Oops, let me just write something. PowerPoint's not cooperating. Okay, so in this particular example, the domain would be all the values that I can plug in for X. So anything that I can plug in there and add 6 to would be in the domain of that function. X is also called the independent variable. And it's called the independent variable because typically when we're graphing, we pick the X, or that's typical of a function. We pick the input, plug it in, and get the output. So the input is independent. So the independent variable is what we input. And what you get out of that function depends on what X is. So the dependent variable would be the f of X or Y. You can use f of X and Y interchangeably. So what I output is the range. That's the dependent variable. Y depends on the value of X, or in the function we looked at earlier, Fahrenheit depended on what you put in for Celsius. So Celsius was the independent variable, the input. Fahrenheit was the dependent variable, the output. It depended on what the degrees in Celsius was. A scatter plot is a graph of the set of ordered pairs. So when we graph that table of values, Celsius, Fahrenheit, we graphed a scatter plot. And we are going to be doing that a lot this semester. We're going to graph a whole bunch of scatter plots. So given a set of ordered pairs, can I graph those on the coordinate plane? Of course you can. Okay, let's look at some examples of domains and ranges. So I have a relationship, and it looks like a function to me, defined in terms of a graph. And then I have a relationship defined in terms of a table. What's the domain and range? And these are actually the same, are they not? This table and this graph of plotted points are actually the same values. So I have -5, -7. I have -3, -2. I have -1, 6. Okay, so what's the domain and what's the range? Well, the domain is the set of inputs. It's the set of X's. It's the set of independent values, independent variable values. So our domain consists of these numbers right here. That is the domain. It is the set of inputs. See if I can write this as a set. And I'm just going to list the elements in that set using a roster. So use braces and then just list the elements in the set, and the range is what? This is very messy. -7, -2, 6, -2, 5, and -7. And that is a domain. Excuse me, that is a function. Ugh. That is a function because I don't have one element in the range going to more than one element in the range. Let me back up. I do not have one element in the domain going to more than one element in the range. So this is a function. Every element in the domain goes to one and only one element in the range. Okay, what's the domain and range here? Now, I don't have just specific discrete points plotted. I actually have a nice smooth curve, very pretty curve. But I can see in both the horizontal direction and the vertical direction where this graph starts and where it ends. So if I look in the horizontal direction, horizontal meaning this way, that is horizontal. So the floor of the room you're in hopefully is horizontal. I can see in the horizontal direction that it's this graph starts here and it ends here. So the graph starts what looks to be at -3, and it ends what looks to me to be +3. So in the horizontal direction, this graph starts at -3 and ends at +3. So the domain, I don't want to list all the numbers between -3 and +3. So I would write that probably as an inequality. And you'll see these are solid dots. They are solid dots. And solid dots means that -3 is included. If it were an open dot, it would not be. Solid dots mean that -3 is included in the domain. So it goes from -3 to positive 3. So the domain of this function are all the values x between negative 3 and positive 3. Any input between negative 3 and positive 3, any number between negative 3 and positive 3 could be an input. We could also write this, dadgummit. We could also write this in interval notation. We could write a bracket, a negative 3, comma, a 3. Means the same thing. When we separate numbers using a comma and put brackets around them, it means exactly the same thing as that inequality. They're exactly the same thing. All right, what's the range? So if we go vertical, which is up and down, and hopefully the room that you're sitting in, the wall is vertical. That is a vertical object. So in the vertical direction, where do we start and where do we end? We start here in the vertical direction. That is the smallest point in the vertical direction, and we end up here, don't we? Do we end here? So what is that? I don't know. It's kind of hard for me to see. Looks to be it's starting at negative 25. If I move over to the y-axis, it looks like that point is at negative 25. And where does it stop? Does it stop at 40? That's what it looks like to me. Or we could write that as negative 25 to 40. Means the same thing. This is called interval notation. Where you're just listing the endpoints in the interval. Very, very concise, easy way to write things. And this is a inequality. And it's an inequality because we're using inequality symbols to describe x. X is between negative 3 and 3. It's greater than or equal to negative 3, and it's less than positive 3, less than or equal to positive 3. So it's somewhere in between negative 3 and positive 3. And y is somewhere in between negative 25, maybe that's negative 3, I don't know, negative 25 and 40. I'm estimating because I'm just looking at it on a PowerPoint slide without my glasses on. Looks pretty good. Pretty good estimate. And this one, again, domain is horizontal and range is vertical. So this one's kind of tricky because in the horizontal direction, we're starting here and going that way. So the most positive value is at 4, and then we're going to the left. And this arrow means that we're going indefinitely to the left. So we're going forever to the left. So how in the world do we write this? How in the world do we write this? Well, what we say is anything to the left of 4 is less than 4. So left of 4 is less than 4. Correct? Anything to the left would be less than. So anything to the left of 4, we're going to use a less than symbol, and I'm going to use less than or equal to because that is a solid dot. So we're going to use equality because it's solid dot. And we're just going to put an X in there. So anything, any value that's less than or equal to 4 is in the domain of that function. Anything, I mean, 0 is in the domain of that function. Negative 8's in the domain of that function. Anything that's to the left of 4. And in interval notation, where does this interval start? Well, it doesn't start anywhere. It continues on to the left indefinitely. So we give it an endpoint of negative infinity. So all the way to the left, as far as you can possibly go, we're going to call that negative infinity, and it's going to stop at 4. So that's the domain of this function. What's its range? Well, it's going to start here, and then where's it going to go? It just continues up indefinitely. So it's going to start at 4 and continue on up. So anything that's bigger than, excuse me, that's not a 4, that's a 0, Lisa. In the y direction, the x-axis is 0. Anything bigger than 0. So anything above the x-axis or on the x-axis is going to satisfy this. Anything from 0 to infinity. So any y value that's greater than or equal to 0. And the way we write that in interval notation is we start at 0, and then we continue on forever, and we use infinity. Okay, I'm out of time, but I'm going to mention one thing. You'll notice that I put a parenthesis next to infinity or negative infinity, and I put a bracket next to the 4 and the 0. That's because infinity is a concept, it's not a number. It's not something you can ever reach. You can never put a bracket next to infinity because you're never going to get to infinity. There's one other thing I want to mention. I know I'm out of time, but I'm going to mention it anyway. When you write interval notation, you always write from the smaller number to the larger. It's always left to right, or bottom to top. Always the domain is left to right. So it's negative infinity to 4 because negative infinity is to the left of 4 on the number line. The range is always from the smallest to the largest, smallest, largest. So the smaller number is 0 because that's where it starts, and the larger number is infinity. It continues on forever. So we're going to talk about that being from 0 to infinity, smaller to larger when we're talking about range, and smaller to larger when we're talking about domain, left to right. Are there any questions today? All right, we're going to finish this up on Wednesday, and we'll discuss section 1.2 on Wednesday also. I'm going to upload this to YouTube here in a few minutes, and I'll send the link out later this afternoon. All right, if there are no questions, I'll see you Wednesday. Bye-bye.